Good morning.
Good morning.
Did you enjoy additional
weekend?
Yeah, additional weekend. Yeah, we missed a lab, but I think
Yes.
it will be possible to cover this.
Oh, Uncle.
Cover.
Yeah.
Is it possible? Is it possible to help projecting on the?
Then I'll get it. Hi, Dr. Kelly. I have two homework.
Oh, okay. Then you'll get double credit. Today's meeting is completely. Sorry. Today's meeting is completely useless in a sense of the overall goals of the course. So it will be beneficial as a little illustration to what we are doing, and it will be helpful if you are looking for satisfying curiosity and overall growing the baggage of background concepts. But the course can be done without it. If one day I need to squeeze it into like a course in a month or half semester, this will be omitted. Before we go to this useless lecture, let's chat briefly about organizational things. We have a limited time for semester. We need to finish by a certain time, and there is a program. The meeting yesterday was missed, and next week I'm on the conference. The lectures will be administered. I will be coming, I don't know, maybe facing one screen and presentations in another, or you can completely not see me, but I will connect electronically. This facility allows it. And you have the link, right? If some of you do not want to appear in class, you also can watch it. It's scheduled regularly at the class time.
Send us the link, please.
Huh?
Send us the link.
Okay. Yeah. At least I need it for myself to connect. When I'm here, it is better to come in person because you can interact. But and if you are on the link and you are not speaking, it's very wise to turn the microphone off, because otherwise, if like Each of us will connect through internet. We all put microphones. There will be echo immediately. So I will be away next week, but lectures will be administered. And for the lab, I will ask Dr. Han, a postdoc from my group, to show it. The plan for next presentations is first Thursday of March. And one of the handouts is the list. You don't need to sign up right now. We can do it later, but you may read the list of this. Of the subjects and decide what you would be more willing to present. So we will have 3 labs before you present, 1 by Dr. Han and 2 by myself. The last one will be just the night before the presentations. But this is useful but not critical aspects. For research projects, we will be doing different software, and this is more important if you are doing small molecules. So this we will do electronic structure with steps. Okay. So I think going over the subjects in 3 labs is possible. And I also can share the recordings from previous years, which I hope every year it is better, but maybe not substantially. There is another handout, is a homework, which will be extremely quick. There is a chance that you complete it before we depart here instead of leaving it as a dessert for the weekend. So it's really a couple of minutes. So if the concept that we will discuss in this useless lecture will come close to your hearts, you'll do it in like 3 minutes. If not, you just meditate and do it in 10 minutes. So it's really quick. And since I will not here, it would be the best would be just to scan and send as an email. Okay. Now, who we are and what are we doing? It is a computational chemistry class. We want to model materials and molecules, predict their electronic properties, and their properties in general. And we recognize and acknowledge that small objects have quantum features, wavy nature. So we started with multi-particle molecular Schrödinger equation, and then we did the separation of electronic and nuclear variables, which is valid if non-elevated couplings are dropped, and we do not look on combustion and explosion if it is like low temperature or at least room temperature, so there are no reactions. For nuclear degrees of freedom, we accepted the Ehrenfest theorem and agreed to follow one of the expectation values of the position, and then we come to equations that look like Newton mechanics. And now we are focusing on electronic degrees of freedom, and we will look on the simplest possible theory for electronic degrees of freedom, which is called Hartree-Fock theory, which is so simple compared to other theories. I'm not telling that it is super simple, but it's simpler than anything else. That it is typically included in advanced courses in physical chemistry, and you may have seen it. The Hartree-Fock theory is again useless for practical computations because it is known to bring substantial error in whatever it predicts. Typically, it increases the energies, especially it makes blue shift to the color of any molecule. But it is very logically organized and relatively simple theory, and it serves intellectually, logically as a cornerstone for any other developments. And if we go over the concepts for the simple theory, the other things will be much easier. We'll use it as a stepstone to go further. You may have seen Hartree-Fock theory equations in textbooks or in scientific presentations, it can be delivered in 15 minutes instead of 1 month. But we are going very slowly but surely because there are a couple of background concepts that serve as a little components to cook this Hartree-Fock theory. And if we go over them and make ourselves comfortable with these concepts, we will be feeling better. Instead of memorizing equation, we will know the essence and then we can discuss it. And the practical part of the labs that I hope you will vote to present in 3.5 weeks, will be computational solution of Hartree-Fock equations. So in class we discuss equations, in the lab we solve them practically. So last time we were discussing atomic orbitals and antisymmetry principle, right? Before slides we should talk, otherwise it will be boring. It's possible to lose the track. So we need to solve electronic part of Schrödinger equation, molecular Schrödinger equation, and wave function depends on positions of all electrons as independent argument, right? And there are too many of those. We see immediately that we do not have computers that store more than like petabyte or like 100 petabyte, and it is just very small molecules that will occupy all space just for saving solution. So we need to divide and conquer, and most reasonable idea is to represent multi-electron wave function as a product of one electron wave functions. The best candidate for one electron wave function is solutions for hydrogen atoms, and you may have agreed that the website ptable.com is a very good illustration to see these solutions of hydrogen atoms, right? So there are like 3 quantum numbers, principal, orbital, magnetic, and there are this flower-like these petals structures. So we are good on this side. And then can we just multiply several atomic functions and use it as a basis for wave function of material or molecule? Do we lose anything? Yes, we do, because there is a Pauli exclusion principle, there is our Pauli principle that there is no, in one object, there are no 2 electrons with the same quantum numbers in the same state. And in order to respect this rule, one can compose antisymmetric wave function. And if antisymmetric wave function is composed, then it mandates fulfilling of this Pauli exclusion principle. So even if I try to violate it, I fail. It will just, no. It will be 0 instead of wave function if I try to do something against it. And shorthand notation for antisymmetric wave function is Slater determinant, right? When the rows, there are different orbitals. On the columns, there are different electrons as an argument. One takes determinant as a linear algebra. So, where this antisymmetry comes from? Is there any additional way to set up this specific form for antisymmetric wave function? Like we checked that this form is helpful, but we didn't derive it. And today's lecture will show an attempt to derive this form. Another goal of this useless lecture is to correct a statement from the previous one. Previously, no one caught me lying or being not precise. I was telling that state of electron and hydrogen atom is specified by 3 quantum numbers, right? Would you like to correct me now?
4.
Huh?
4.
Yes. And what is the fourth one?
SPDF.
Huh?
SPDF. No.
No, SPDF, it's all, it's angular quantum number, right?
Is there a spin?
Spin, yes, correct. So we will just discuss concepts, and you can find it by reading the homework based on what we do. So we will review basic background concept behind spin and try to make connection between spin features and Pauli exclusion principle as possible. Any objections or questions? So there is a plan to arrive to this slide at the last minute of the meeting. So on the left, there is a antisymmetric wave function that you agreed, right? So function 1, function 2, or function f, function g, electron 1, electron 2. And here again, electron 1, electron 2, but functions are swapped, right? Electron 1 has spin up, spin alpha. Electron 2 has spin back, b, like up and down. Electron 1 has spin down, electron 2 has spin up. And if two spins 1/2 are added together in such form, it will be singlet state with lowest angular momentum. There is an analogy between these two things, and these symbols look a little, I wouldn't say ugly, but too many new symbols. And it will be not critical for success of the course, but maybe helpful if we cover these symbols where they originate from and what are they used. But if you are tired or busy with like other things, this is not the most important lecture. You can lean back and relax. When it will be really important to focus and memorize, I will let you know. This is more like entertainment and background. So here's what we did last time. And I'm a little disclosing what will be the homework in like a week and a half. Build oligomers of titanium dioxide and find total energy with Hartree-Fock. So the logical stream of our chapter on Hartree-Fock goes from Slater determinant, concept of mean field, correlation exchange, and then electronic structure by Hartree-Fock. The concept of spin and analogy with Slater determinant is kind of merging. We are deviating from main logic and then return. But later on, it may help you, especially if there is a probability that you need to do projects on transition metals, which have unpaired spins. Like if you do corrosion of metals, you deal with transition metal. If you plan to do any magnetic materials, then spin is necessary. So it's kind of background concept that you may benefit later. So there is fourth quantum number, right? So let's discuss what is spin. Please try to answer to yourself, and also you may want to just verbalize it.
Rotation.
Good? Everyone agrees? Huh?
The direction.
I didn't catch what you said.
Rotation.
The
So-
direction of rotation.
Huh?
The direction of rotation.
This is a very good educational concept to discuss it, and if you will pursue academic career, it is a good starting point. Like, bring globe in class, spin it, and tell like, here is the spin. But if you are writing a paper presenting your results on scientific conference, never tell it in public. This is a good educational step, but it is not quite correct. If previous years there were some physics majors in this class, and they told that in physics program there is a problem for everyone to solve. Like, what if the electron has so big or so small diameter? Which speed should it rotate around itself? What would be the speed on the surface of electron if it is a like solid ball to reach angular momentum that would correspond to this spin? And the answers are much higher than the speed of light. So it's only an analogy. Do not tell it in public. But the analogy is as follows. If you have a charged sphere, if it rotates, and moving charge creates what? Magnetic field. Right. Magnetic dipole. And depending on direction of rotation, it will be magnetic field will be in the opposite direction. So it is supported by all experiments. So this concept was designed to explain existing experiments that standalone electron experiences this, exhibit this properties, and it does has its own angular momentum. But this angular momentum corresponds to only certain value. It cannot be continuously changed, and it is normal in quantum world. If we speak about rotations, it can rotate only with so many revolutions per minute, forwards and backwards. But again, do not speak about revolutions in public. Correct way is to say just discrete values of angular momentum. And they have values of Planck constant over 2. Planck constant has dimensionality of angular momentum, which is distance times momentum, or energy times second. If we believe in Pauli exclusion principle, if we draw atomic structure of hydrogen like atoms, like 1s2, 2s2, p2, remember that, right? Why in the lowest cell we have 1s2?
One electron is spin in one direction and the other has in the other direction to balance each other.
Exactly. So each of the spins have different set of quantum numbers.
Yes.
So Pauli exclusion principle is correct. So this spin is these two electrons differ by the value of the spin. So only two discrete values: angular momentum up, angular momentum down, and there are multiple notations. We don't basically it doesn't matter which one to use. One can tell plus and minus, or up and down, or 1 and 0, or maybe plus 1/2 minus 1, or alpha and beta. Historically, in the computational chemistry community, alpha and beta is traditional notation. But if you decide to use other notation, no one will persecute you for this. Just to agree with text. No objections. You believe in spin. Okay. So, if we do have a system with spin, what are our natural questions? What should we do with it? What can we ask ourselves? Is there a physical mechanism and associated mathematical procedure to change the direction of a spin? Is there a way to make it to flip around? maybe apply strong magnetic field or something. Or does anyone practice nuclear magnetic resonance experiment? You didn't?
NMR?
Yes, NMR.
It's been a long time.
Okay, but there is one vertical magnetic field in strong permanent magnet, and there is a radio frequency transversal, and they are used to flip the spin. And so there is a physical mechanism. Excitation with radio frequency if the energy of spin is split by magnetic field. Is there a mathematical language to describe this flip of the spin? You may look at me as an idiot. Like, there's just 1 and 2. What's the math? It's just what, 2 states, right? What is the question? But if we want to formulate equations that later we solve either by pen and paper or putting into the computer, if there is a process where spin is being flipped, one needs to be a little bit more formal. And also, I was consulting with one of my colleagues about, like, I do not have motivation to give this lecture. It is useless. How to explain to attendees of the class that they are recommended not to stand up and live, but sit and listen. What's the benefit of a spin? So if you read news, and if you just follow popular science, you hear about 2 fun things. Well, you hear definitely of more fun and maybe different things, but related 2 fun things related to spin: superconductivity and quantum computers. So the concept of spin and their flip is important to NMR, to superconductivity, and also for information storage. And in these processes, one does need to describe spin from quantum point of view with a concept of superposition. When the spin is simultaneously in state up and state down with certain probability. And then it is not as silly to ask how to mathematically represent the spin up and spin down. And what if it is like 25% up and 75 down? So one needs a little bit more background. So we need to represent it mathematically, and we do need to create, design mathematical procedures that will describe flip of the spin. And I'm making a little step forward. The next, after we become comfortable with these things, we may want to find a procedure that will determine percentage. If we set up like wave function for spin, by which procedure we read this wave function. In these simple things, it's like playing card with open game. You can see the result. But what if we play not open game? What are the procedures? I have very clear mind what to say. I just try in the best way to be convincing. Basis. If we have 2 possible states, it means like 2-dimensional space. You can make 1 step in x direction and 1 step in y direction. Then it is a plane with vectors. and the length of the vector is so many times x, so many times y. And the vector composed of both of them. And then any number of two-dimensional plane can be stored as two numbers, x and y projections. If spin has two possible values, alpha and beta, and maybe some superposition between them, can we speak about projections on this spin directions, same two-dimensional plane with two numbers? With which probability it is in spin up and with which probability spin down? Two numbers, plane. And two-dimensional vectors can be saved as like two numbers, which can be saved as either just numbers with comma or as a vector, two-dimensional vector, as row or column. Make sense? The little angular bracket originates from so-called direct notation. And I think we discussed it before. In quantum theory, often one needs to find expectation values, find probability distributions, and one needs to find wave function absolute value squared, right? But wave functions are like in zoo. They may have infinite number of dimensions. They may have two dimensions discrete, and one needs some unified treatment for them. And direct notations allow to speak about some general trends without specifying number of dimensions in number of degrees of freedom in wave function. And these angular brackets are used for this thing. Like if one multiplies wave function by itself, integrate, it is replaced by left bracket and right bracket, and one places a function here. If one writes the word bracket, one can split it into two parts and call it bra and cat. Bra for wave function conjugated, cat for wave function without conjugation. Here column vector, here row vector. So it is for integration. If one swaps the order of bra and cat, it will be an operator.
Quick question.
Oh, yes, yes.
What's the star on the wave function? What is the indicator of?
Conjugation.
Say that again.
Conjugation.
Conjugation.
If
Okay.
if there is a formula for this wave function, you replace sign in front of imaginary unit. You flip the sign in front of imaginary unit. If it was plus, you make it minus. If it was minus, you make it plus. Five minutes for a silly thing. Suppose, and it will be very much connected to the spin. Consider a bird, an owl. Consider a wizard. And the wizard makes hocus pocus and converts it into a skylark. Okay? So we need to do the same with the spin. Take spin up, make hocus pocus, and convert it to spin down. Same like in the nuclear magnetic resonance experiment. But you got the concept, right? Mathematical procedure to flip it. Now we need to put formulas behind it. So we start with cat vector of the state of our object is full. We apply operator, and we get cat state of the object, which is skylark. If we have all and all as bra and cat vectors, we can convolute them, and since they coincide, it's like normalization. And all absolute value squared integrated will be 1. So if the it's like scalar product. If the same vector is multiplied by itself, it will give 1. Right? 1. if we multiply scalar by itself, make scalar product, it will be also 1. If we multiply an all by scalar, the scalar product of all and scalar will be 0. Right?
Yeah, so 9 to 0.
Mm-hmm. And if you swap the order, it will be still 0. Now, what if we make the dyadic product, which means we have bra and cat swapped. Like here is the column, here is the row. Such construction with swapped order of bra and cat with row multiplied, column multiplied by row. In linear algebra, you typically multiply row by column, right? You multiply two vectors and get one number. If you swap the order and multiply column by row, you will get a matrix. If following multiplication rules. In quantum theory, it will give an operator. An operator, a wizard, that will convert one thing into another one. So this one will convert all into the all. Nothing interesting. But this one will convert all into a scalar. And I'll illustrate. So the wizard is represented by this operator, direct product. So here it is bra, cat, cat. So the operator is, or wizard is represented by bra and cat swapped. Now, when the wizard acts on the object, when the operator acts on the wave function, we may identify that at initial step, we distribute these three objects, like first two comes together and then gets another one. Now let's look on them in the different order. First comes separate and we look on this as a one. Right? And before we agreed that bra and cat with the same object is a scalar product that will give
1.
1. Right? Then here we will get scalar product that is equal 1, and here we will get a scalar. So it is a mechanism how alls become scalars. Right? Since it is equals 1, we can skip it. So you already got the mathematical procedure for spin flip, but we need to be a little bit more less cartoonish and more convert it in a boring mathematical symbols. But there will be no more new ideas. So if we have a cat like O, and we act by a wizard, O and scalar, we look on the blue box, which can be considered as scalar product that gives 1. And as a result, we get a scalar. So by acting of the spin flip operator, we are getting different spin. So it was up, we apply operator, and it gets down. Look at your homework assignment. Does it look similar? It may have open, like minus here, beta here, something a little different, but you see the similarity, right?
What is the meaning of subscript 1?
Thank you for asking. One spin is cool, but it is not enough. you are so intellectually strong that you need more food for thought. Most molecules and materials have more than one spin. So this will be a raising operator for first spin. And we will have also raising and lowering operators for spin for second spin.
So for S, so like the positive, you know, when we have positive and negative, or are those representing?
Flipping spin from down to up and from up to down. So if you have minus, we just flip things here. Then it will convert beta into alpha. And if you apply this S minus to beta, we identify scalar product, bra times ket, which is 1, and then it will be alpha.
I have a good.
Yes, please.
I can change the convention, am I right?
Huh?
I can change the convention up and down.
Oh, use any convention you like.
Yeah, I can. It's on my own choice.
Yes,
am I right?
yes. Now, if we are in the NMR experiment, the spin can be in average, it can be directed not only up and down. There is a probability that it is a superposition. And if you are speaking in analogy to two-dimensional vectors, right? Vector is represented by two numbers. So we represent vector as basis function first, 1, basis function second, expansion coefficient 1, expansion coefficient second. Same as in the two-dimensional plane. We have unit vector in x direction times projection. Unit vector in y direction times projection. So it's just a representation of a vector. In quantum theory, these projections have meaning of the amplitude of probability. Those are numbers that upon being squared they give probability. And let's formulate a question. How we need a mathematical procedure that will generate this C sub beta star times C beta, which will mean the probability that spin is in state down. So how to, again, if I would be sitting in the class, I would look on the instructor as on the English. There is a number, what's the problem to take it squared? But it is if you play open cards. What if it is a mathematical procedure with unknown values of numbers? So how to extract this product out of this wave function? What if we try to do two operations one after another? First, convert from up to down, and then from down to up. It should be like changing nothing, right? From up to down, from down to up. And if you do it in a mathematical way, we do this two wizards. From beta to alpha, from alpha to beta, and then the four objects together. Let's look on the one in the middle. It will convolute, scalar product gives 1. And then it will be operator that converts beta into beta. And nothing else. If there will be alpha, it will not affect them. It will give 0. Exhausted? Bored? Like, we came here to model materials, and here is the boring math. So, we do have this operator, and we need to have two wave functions, cat and bra. So in cat we have cat of the basis functions and expansion coefficients without star. In bra it will be basis functions with angle in different direction corresponding to row vectors and expansion coefficients with star. And the answer on a question will be find a matrix element of this spin wave function. Bra, cat, operator inside. Same as when we were going from nuclear wave functions into molecular dynamics, we were focusing on Heisenberg equation of motion and expectation values for expectation values. So, bra, operator, cat. There are product of three terms. Right? First and last are brackets with two components. How do we open the bracket? Right. First times middle times first. First times middle times second. Second times middle times first. First times middle times last. Right? There should be four terms. First, middle, first. First, middle, last. Right? So I'm not yet ready to process it. In order to find the answer, I need to convert this S plus and S minus into Bryant cat notation because it helps to do things quicker. So middle part will be cat beta, Bryant beta all the time. And now we can look. So that as soon as we have at least one non-collinear component, it will give scalar product 0, and we can cross out the term. So this one is 0, we cross out the term. This one is 0, we cross out the term. This one is 0, we cross out the term. This one is 1, this one is 1. So the answer will be C star sub beta, C sub beta. So if you find expectation value of projection operator, it answers with probability to find spin in a certain state. Okay?
So for this state, it is known. It's going to probability is going to be 1. For this state,
if the spin was 100% down, the answer will be 1. But if it was like 50-50, it will give this probability. Yes. A little bit more things of our useless lecture. If we, well, now only when Berlin accepted the motivation related to nuclear magnetic resonance. But it is a powerful technique used in chemistry to characterize molecules. How do we know how do the spin up and spin down components are oriented in a true Cartesian space? Our space is three-dimensional. What does it mean, spin up and spin down? It is related to direction of magnetic field. Before we apply magnetic field, it is not known what is there. But after we apply, we still, there is a way to convert this spin algebra and observables of our real world, where spin generates magnetization, and magnetization can be oriented anywhere in three dimensions, right? So if one assumes that spin up and spin down are represented by these operators, x and y, this imaginary part, then it enables conversion between abstract concepts and magnetization, which is observable in the real world. dictionary that we basically covered. So it's just a summary. So the cat vector is the column. If it is alpha, it is like 0, 1. If it is beta, it is 1, 0. Unit vector in a certain direction. If it is bra, then it is, instead of column, it is a row. Again, 0, 1. Generally, superposition spin wave function is alpha plus beta with expansion coefficients. If it is cat, then it is vector. If it is bra, then it is a row. So it all starts. The abstract notation for this raising and lowering operators is a matrix with only one element equal to 1, all others are 0. And originally all the things were designed in matrix formulation, but this Dirac notation is a little easier because it allows skylines. Now, we are approaching the end of the meeting. So this torture by abstract concepts is limited. We'll finish soon. Suppose that we do have two spins, each of which can be up and down. Then we are coming to the same discussion, how to represent a wave function of two independent variables in the best way. So one can try to represent it as a product of one spin wave functions. So if you have two spins, each of which can be alpha and beta, right? Then any possible wave function of two-spin system can be represented as in this form. So both first and second up. Both first and second down. First up, second down, first down, second up. But since we allow first and second spin to be in a superposition, we do not know for sure where it is. We need to allow all these terms, right? And the question is, what will be the expansion coefficients in front of this basis functions? And instead of this product, it will be more reasonable to combine them in the coefficients this way. So the question is, where do we find these coefficients? Which combinations of spins in these two-dimensional spin functions are legitimate? One of the procedures, and basically I'm repeating material from like quantum theory class rather than computation. Basic procedure for spin is to find eigenstates of square of the total spin operator. It's related to orbital quantum number. And by finding eigenstates of the total spin, by diagonalizing, formulating it and finding its eigenstates, since there are 4 basis states, there will be 4 solutions. And for the system, 1/2 and 1/2, maximal possible values for total spin will be 1. Minimal absolute value will be 0 if they subtract. When total spin is 0, it is singlet. When total spin is 1, it is when it's 1/2, it is doublet.
Up and down.
And if they add constructed with like 1/2 minus 1/2 will be 0, single. If it is only one spin, it is a doublet because it can have 2 projections. When there are 2 spins with total value 1, what's the name? You know it. It is the ground state of the oxygen molecule. let's, okay, wash my hands. No, I'm not going to lie. Just please count out loud.
2, 3.
Okay. Now let's change the words. Single, double, triple.
Triplet.
Yes. Triplet. Triplet state because it's triplet degenerate. So when one finds eigenstates of the total angular momentum, there will be 4 solutions: 1 for singlet and 3 for triplet. And triplet has a minimal total angular momentum. Therefore, it is more popular in nature, and therefore we select this solution. By finding this eigenvalue solution, one finds values, which will be either 1 or 0, and one finds eigenstates, which will be values of these coefficients. So for the triplet, it will be first coefficient 1 are the zeros, last coefficient 1 are the zeros, or first and second equal with plus sign between them. For singlet, it will be first 0, last 0, and 2 middle coefficient equal by the absolute value, but opposite by sign. And since we mandate the wave function to be normalized, so the total probability will be 1, they should be 1 over square root of 2. So if you put here 1 over square root of 2 and we remove last 2 terms, we will obtain the functional form where first spin is up, second down. Second spin, first spin down, second spin up. And this functional form reproduces the antisymmetric wave function. I'm not telling that it is a theorem, that because of that we get this. We got this shapes of the wave function from different logical trains, but they come to the same shape. And the goal of this meeting was to reduce spin, which will be a part of some calculations for magnetic material. It will be part of calculations. And another thing is to seize the logical connection, that the antisymmetric form of the wave function is not only a unique thing for when we consider wave functions in general, for antisymmetry principle. It comes naturally if you consider multi-spin system. Yes?
If you can please go back.
Back?
Back. Yes. You said that the first and the fourth will be 0. The value of the coefficient. Okay. So, and you said the second and third will be the modulus with sign different.
Yes.
Then why you choose 1 by root 2?
Because it gives the minimal value of eigenvalue.
Okay.
So for the answers will be 0 and 3 times 1, 1, 1 for SS squared. If you take the minimal angular momentum. I was asking this question to myself as well.
Yes. Thank you.
So we did a little deviation from straight logic, then we'll go straight forward. Thank you for interest, dedication, and patience. Meeting is done.
One question.
I'll answer any questions.
For this system, we assume the 2 electrons are in the same plane. It's for a 2-dimensional system, right? Or if we extend to 3-dimensional, can we use such equation?
I understand your question. I will cover and formulate it. The analogy with 2 dimensions is not wrong, but it is not quite the same as the geometry on the plane, because this C sub alpha and C sub beta coefficients are allowed to take complex values. So it's two-dimensional complex plane, and complex value has already two components. So in some sense, it is like four-dimensional probably. But there is a way to convert these two complex values into projections in three-dimensional space. So the algebra of spins is correct, and it will be useful. It is used if you need observables for real world.
Because 3-dimension doesn't have the complex.
Our regular two-dimension descriptions, but two dimensions for spin, they have complex. Mm-hmm.
Number.
You can immediately forget, well, complete homework and immediately forget this subject if you never plan to focus on transition metals and magnetic materials. If there is a chance that your career may focus on them, then sooner or later it will come. And some calculations in the lab will relate to unpaired spin.
Thank you, Dr. Dimitri. This was very important for me, actually.
Oh, okay, thank you. I thought it would be a waste of your time, and everyone was like, why did I came here?
Thank you.
Thank you.
Have a good weekend.
You too.